Good morning, everyone. My name is Marcel, and I'm very excited to share with you GlobalConfusion, TrustZone, Trusted Application ODAs by Design. This is work we did at EPFL in the HexHive laboratory, and I was collaborating with Philipp and Mathias on this. So on our modern mobile devices, we run a bunch of applications, and these applications process sensitive data that is exposed to threats like a malicious app being stolen or a thief just stealing your device. And as a second line of defense, vendors decided to have this isolated execution context called the trusted execution environment that hosts the most sensitive services, like your biometric identification, your authentication with PIN pad and password, and the cryptographic keys that are used in many services. This technology is typically based on ARM TrustZone. So in one of the other talks we had here at USENIX, the Spill the Tea study, we looked at rollback prevention. Check out this talk for the details, but in this talk, the motivation was that we need a vulnerability, a security critical vulnerability in one of these trusted modules called trusted applications. And this talk here now is exactly about finding these security critical flaws. And the funny anecdote is actually that these two papers have been won, and during one of the cycles at CCS, this paper, as it was still won, was rejected, and the reviewers told us basically to make two papers out of it because it would distract too much to have this paper inside of the other. So thanks for that. To give you a little bit more context, I'm going to drill a bit into the architecture of modern mobile devices. So typically you have a so-called normal world, the rich execution context, where on Android you have your Linux kernel running in the privileged mode and some applications running in the application, in the user space. And those applications can be clients to the trusted execution environment. And in the trusted execution environment, you actually have an entire operating system plus user space stack itself. And the idea is that these client applications, via some logical channel, can request sensitive services from these trusted applications. So now, when this all started, vendors deploying trusted execution environments on their devices, it was kind of Wild West. Like the whole ecosystem was very, very fragmented. And then GlobalPlatform, this industry association, came up with the idea to define specifications to kind of standardize a couple of these interfaces. And the one that is of particular interest in this talk is the GlobalPlatform Internal Core API, which is, you can imagine this as the kind of POSIX API of trusted application developers. Okay? So, and now I want to go first, so you can find these specifications online. They have all of these APIs in there. And it's the de facto standard that is used in all of the trusted applications you can find on modern mobile devices. And I want to go into one specific API here, which is this invoke command entry point. Don't be scared. I will walk through this C code example step by step to kind of highlight the point, what we were looking for here. So we take a look at the signature first. You see 4 parameters. The first one is for kind of storing session-dependent data, which is not super relevant for us. And then we have 3 more parameters that are actually untrusted data and directly controlled by attackers. One is the command ID. So trust applications typically implement different command handlers, and the command ID is kind of the identifier to choose one of them. And then we have the 2 parameters that are of particular interest for this talk. So the parameter types determine the types of the next parameter, which is this array of this TE param struct, which you can see here on the right. And you can choose basically between one of these parameters being a memory reference or a value. And if you have done like a little bit of security in software, you can think, okay, this already sounds very, very interesting from a design perspective. But let's walk through this example a little bit more to really understand what this is about. So in these specifications, GlobalPlatform suggests you could just check these types. And then you would make sure, okay, the parameters that I'm expecting are memory references. In this case, one of them being an input and one of them being an output memory reference. And if that doesn't match, the trust application would safely abort. So the implementation that I'm showing you here is basically an easy echo trusted application. We have an input parameter and an output parameter. Both of them are memory references, and we are copying the contents from the one buffer into the other and just returning it to the users, just for illustration purposes. So now, unfortunately, the check that I've shown you before is optional in the specification. Okay, it's not enforced, meaning that as a developer, when you implement a trusted application and just forget about this check, well, everything works well if you provide the right inputs. But if you intentionally, from an attacker's perspective, just pass a value and the trust application is processing this as a memory reference, you can imagine that here in this memory move operation, you basically can pass arbitrary pointers into the address space of this trusted application. And this is exactly the bug or the vulnerability pattern that we were looking for in the wild, which brings us to our prevalence study. So kind of after realizing that this bug is reoccurring all across the ecosystem, all across vendors, we wanted to know, okay, how severe is this really? So we created a data set. We looked at the 5 topmost Android phone vendors, which comprise 65% of the global market share. We downloaded terabytes of firmware images, around 545 of them. We have 54 devices covering 5 different TE implementations in our data set, and we looked at trusted applications in a time span from 2016 to 2024, so very recent. In total, we looked at about 14,500 trusted applications. You can imagine this is a lot of data. All of this is proprietary, like ARM binaries. And we, of course, did not do this analysis manually. We built a tool that helps us, GPCheck, which is a static analyzer on top of Ghidra, which is an open source reverse engineering tool, which was released by the NSA a couple of years ago. And we use this to carry out this prevalence study of this bug pattern. And we suggest that vendors now can basically use it to do some post-production vetting to make sure that they don't deploy vulnerable trusted applications that have this vulnerability pattern on their phones. So all of this is open source. You can find it on GitHub. So let's come to the results of this prevalence study. So out of the original corpus of trusted applications, we found that like around 6,900 were actually global platform compliant, meaning that they implement these APIs, which are prone to this vulnerability pattern. And we discovered that 850 out of these were actually vulnerable. And that boils down to 33 unique vulnerable trusted applications. So 9 out of these 33 vulnerabilities were actually publicly known. So we found either like CVEs assigned or security bulletin entries for these. 10 of them were silently fixed by vendors. So there was no advisory that the TE has been vulnerable for some time. And we actually found 14 O-days in the latest versions of phones that you all guys might be using. And that was very interesting because it gave us a bunch of CVEs where the numbering authority is not MITRE, but like actual companies with like a technical review behind it. And we got a little bit of money out of it, like somewhat more than 12,000 US dollars as a bug bounty for this work. So just to give you a visual for how severe this bug is. So the first instance that we saw was one of Huawei, somewhere late in 2016. Then a bit later, in beginning of 2018, Samsung kind of realized that they have this issue. Then I guess someone realized that might be a vulnerability pattern, so they fixed 9 of these in their trusted applications. And you would think that, okay, they really got it at that point, right? But in the future, we kind of saw, well, not so much, no, and again, no. But Samsung is not the only vendor who was affected by that. We have a bunch of bugs by Xiaomi, and then Oppo and Vivo were affected. Here we have another one by Huawei, and then I think which really drives the point home is our tool that affected like cross-vendor kind of O-days, more or less readily exploitable to get a foothold into the trusted execution environment. So that's kind of like a design-based issue, and we wanted to do something about it, so we suggested a mitigation, which is also in the paper, and we wanted to change this kind of fail-open design, right? Just a missing check into a fail-closed design. And what we did, we changed the design in a way so that the check for these types is just mandatory, and the trust application would just abort in a fail-safe way when the proper check is missing. We sent this proposal, this mitigation, to GlobalPlatform. They were really happy to read about this, also the empirical analysis behind it. And now this entire draft is under review within GlobalPlatform, and we really hope that our changes make it into the next specification to, in the end, secure the future trusted execution environment implementations. So the good thing about our mitigation is that the changes we made don't affect the external API, so it is backwards compatible and should be kind of easy to adapt for vendors. All of this is open source. You can find it in our GitHub repository. We based this on OPTEE, which is one of the open source trusted execution environment reference implementation that you can find. So with this, I'm at the end of my talk. You can find the paper using this QR code. Our code is online. We got all the 3 artifact evaluation badges. And if you want to talk about global confusion and trusted application compromises, feel free to reach out. Thank you so much.